So we're going to talk about area of a surface of revolution, which of course you might be saying a surface of what? So let's talk about what is this. So you take some curve and then you revolve it all the way around an axis. And so if you think about then just that idea of revolving it and having that come out of the screen, you could probably imagine some sort of like solid 3D object. And so we have a whole bunch of ideas of like the solid of a revolution and using integration with that. So now instead of having this like whole filled in solid here, what we're interested in is just like this outline, the boundary of it, okay? So revolving only the boundary curve creates the boundary of a revolution, i.e. we call that the surface of revolution. So it's literally the surface of that solid that we're thinking about. So let's talk about what formulas do you need for this, because of course it matters if you're going around the x-axis or the y-axis. So if you're going around the x-axis, you're going to want to have your graph in terms of f of x. And so the formula for that is going to be you have to have some function greater than or equal to, sorry, I forgot the 0 right there, my bad. So if the function f of x is greater than or equal to 0 is continuously differentiable on some closed interval, then the area of the surface generated by revolving y equals f of x around the x-axis can be thought of with these two formulas. So of course, if we're trying to differentiate on an interval, it's going to go from a to b here. And then we've got either 2 pi y times the square root of 1 plus dy dx squared dx, or 2 pi f of x times the square root of 1 plus f prime of x squared dx. So either one of these formulas, you can think of this either way. But so also in the work that I've been doing kind of in this series in Calc 2, some of this formula should already feel familiar. So if I think about now context specific, so I've got the interval a to b and I've got my function f of x and then I revolve it or whatever. So I've got this formula, right? This 2 pi f of x and then this square root function. So that square root function, so just where does that come from? Do you remember what that is? So we actually saw that being kind of our arc length formula. So we've already got the arc length portion of this. That is covered in the formula, right? But what's missing? It's now missing this part. So like this will capture just that boundary, but then how do I capture the fact that the boundary now is moving around? Okay, well, that is going to be this other part of the formula. So this f of x, this kind of like acts almost as like, so from here to here, right, this is going to be f of x. So if I have this 2 pi f of x, that's going to account now for that revolution. And I kind of think of this 2 pi f of x. So this is a fancier way of, this kind of relates like to the area of a circle, right? Except now instead of having a constant radius, so the area of a circle is 2 pi r, but instead of having this constant r, we know that this height is changing, right, depending on where we are in the function. So it's 2 pi f of x. So I've got 2 pi f of x, which accounts for that revolution part, and then that times the arc length formula, and that gets us the whole formula. So I'm just bringing that up as a way so you can kind of remember where does all of that come from. And very similarly, so if I want to revolve a graph g of y around the y-axis, so now I need to have a function in terms of y, so very similar. So if g of y is greater than or equal to 0, if this is continuously differentiable on a closed interval from c to d, then the area of the surface area generated by revolving the graph x equals g of y about the y-axis is the integral from c to d 2 pi x times the square root of 1 plus dy dx squared, take the square root of all that, or similarly 2 pi g of y times the square root of 1 plus g prime of y squared. Same idea, right? It's just however you want to view that formula. So very, very similar, right? You just kind of flip everything in terms of y, which if you've probably been working with integration at this point, so not surprising. Okay, so now we're going to just talk about like actually finding the areas of surface generated by revolving the curve around the given axis. And more importantly, we're going to talk about the algebra chops that you need for this type of exercise. So let's start with the curve y equals square root of x plus 1. X will be between 1 and 5, and we're going to revolve this around the x-axis. Okay, so I kind of think it's just nice just to have the formula in front of us. So there it is. So this is kind of what we just need to like plug and chug our way through. But of course you can see, so I've got my f of x, right? I know what my a and b are. What I don't know is what is my f prime of x squared. So I'm just going to take a second to work on this part here first. So y and f of x, in my opinion, they are interchangeable. So I'm just going to take the derivative of this. So if I take the derivative, and actually I would recommend that you just pause for a second and that you write down what you think both the derivative and the derivative squared are before I show you. That's just my 2 cents on how you should be using this video. So f prime of x is going to be 1 over 2 times the square root of x plus 1. So if I were to square that, then I square the 2, which will be 4, and then this square root will go away. So I've got this whole situation here. So now if I just plug in everything into my formula, so there's my 1, there's my 5, 2 pi, so my f of x now is going to be that function, and then I've got 1 plus f prime of x squared. Okay, so at this point, now we need to be a little careful. We need to be clever, and we want to think about how we want to proceed with the problem. So this is always where like Calc 2 can be a little tricky. So we want to think, there's a few options in terms of like what we could do with this formula, because if I look at this formula as is, so I guess we should also just back out a little bit here. This, I can't integrate this, right? Like, nope, can't do it. So clearly something has to happen so that I can integrate this. Now this 2 pi, I don't really care about, right? I can just bring that out in front of the integral. It's just a constant, it's whatever. But I need to really think about what do I do to make this thing integrable. So we're going to think. There's a few options, and sometimes a really good strategy when you're not sure how to integrate is just to look at all of your options and think about what you know. So here's what I think of when I think of options. So I could go ahead, I had 1 over, so remember I had 1 over 4 times x plus 1. So I have a few options of like how I could simplify this. I could go ahead and distribute that 4, right? So that I have this situation here. I could go ahead and I could add this 1 to this fraction, right? So I would get this here. Or I could just leave it all alone. So I'm bringing this up because I think this is like a really excellent example of like decisions that you have to make on quizzes, tests. You kind of have to be a little bit creative and think what actually makes the most sense, because they're all totally equivalent. So the thing that I think of is, so I have 2 square roots, all right? And so the thing that I remember at this moment, square root of x times square root of y, to multiply 2 square roots together, you actually can just, as long as they have the same radical here, you can just multiply that stuff underneath together. So when I look at these and I think about what am I actually multiplying, I am multiplying this part here into this part here, this whole expression, right? And so as I look through these, I think that there is a best choice of what to multiply by. Namely, I think that it is this last option here. So I do not want to distribute that 4 in, because if I were to multiply this across, this x plus 1 and this x plus 1 are going to cancel out, right? So that's the kind of stuff that you want to like pause and think about. And, you know, I'm not saying that you're going to be like perfect at this, or like, oh, if you just paused and magically did that, that would just like jump out at you. I'm also like, I've been doing math for freaking ever. So like I have that foresight, but I want you to appreciate that logic, because this is kind of how you develop that intuition. Okay. All right. So this is the format that I want to use. So what I'm going to do is I'm just going to go ahead and take that x plus 1, whoop, we're going to just distribute it into the radical. Okay. So I have 1 times x plus 1, we're going to have that, and then x plus 1 times this. I'm just going to put the x plus 1 on top of this fraction here, and then I can see, oh, beautiful, it all cancels out, how nice. And so now I'm left with the square root of x plus 1 over 4, and then this becomes x plus 5 over 4. And of course now it's like, all right, wait, what were we doing? Remember, I was looking for something that I can integrate. So in this format here, can't do it. But now in just multiplying them together, this can totally be integrated, right? So that's kind of the whole point, is to turn this into something that you can actually integrate. So, ta-da, here is what we're going to integrate now, right? And so from here, to integrate what we see, I can just use substitution. I can bring that 2 pi out in front. So just to throw out the substitution, that's what I'm doing for my substitution. I'm just going to jump to the answer so that you guys can see it. So, you know, from here, it's kind of like, I'll say quotes with quotes, air quotes that you can't see, boring integration, but I've got all the work up here, tedious stuff with mathematics and all that. Now I am going to show you also what the rest of my calculations were. So hopefully you got the same number that I did, but just FYI, if you want to see the rest of the calculation, here it is. I kind of omitted it, but pause here if you want to read that over or check that out. Okay, so now let's go on to the main event. This one is going to be a doozy, all right? So for this one, so now I've got x equals 1/3 y to the 3/2 minus y to the 1/2, and then y is between 1 and 3, and now we're revolving around the y-axis. So there are a few things going on with this one, my friends. First of all, notice if y equals 1, x equals -2/3, and if y equals 3, x equals 0. Oh my God. Okay, why do we care? So if I go back to that definition that I told you guys, so remember, it's a g of y has to be greater than or equal to 0, and then we went blah, 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 all onto this definition, right? Blah, 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 blah. Okay, remember this part here where I said that this has to be greater than 0? So this is a problem, right? Because I have this negative value. This is not greater than 0. So what we're going to have to do is, and also what this is telling me is then this function's like traveling along these negative values until it gets to this last one here. So we need to just manipulate this function to force it to be positive, okay? So I'm going to use same formula as before. Now everything's just put in terms of y, right? But what I'm going to do is I'm also going to rewrite my function x. I'm just going to slap a negative in front of it. And again, this is just me manipulating this so that I can, because like I need, this is, we're calculating surface area, right? So the thing about this is that, like, since we're calculating surface area, I do actually need this to be positive. So I am within my rights to manipulate this. So if you ever get like a negative surface area, by the way, you probably just want to go back and recheck these conditions here. And you probably had a negative to begin with, and then you would just have to probably put a negative on the answer. So that's just something for you to check. If you ever get a negative with your surface area, just go back and check it, and then you just put a negative in front of it. Okay, anyways, so rewrote that, and so I'm trying to just plug and chug everything in here. So obviously I need to take a derivative. So I'm going to go ahead and I'm going to take the derivative of the function, and then I am going to square it. Now, this function has a lot of fractions in it, right? We have fractions here, we have fractions here. So we want to also be a little strategic in how we're doing this, because let's face it, if you have too many fractions running around, it's like a lot of small numbers, so you might make a mistake. So the other thing that I want to do here is I just want to note, okay, so I've got a 1/2 and a 1/2 here. I actually just want to factor those out in front before I do anything else, because it will at least just cut down on the pure number of fractions that I have running around. Now, I can flip back and forth between these two forms, but for now, since I have to square this whole thing, that is going to make my life maybe easier. Okay, so I have this form here, and now what I want to do is I want to square everything. And this is going to be a moment where, okay, so we're going to square everything, but in squaring this, so I can square this fraction, that's the easy part. The harder part is squaring this part here, because this part here is going to have to be FOILed, my friends. So I am going to strongly encourage you now to pause this video. FOIL this out, okay? This algebra might trip you up. Pause, try it. The worst that happens is you get it wrong, but you will learn more if you make a mistake versus watching me do it perfectly. So pause here, give it a try, hit play when you're ready. Okay, so let's rock and roll. So I'm gonna go ahead and square everything. So like I said, the -1/2 squared, that becomes 1/4. This part here now needs to be FOILed out. So hopefully you've got all your work. I have all my work shown here. So I have this times itself. So if I multiply term by term, so remember the exponents in this case are going to add. 1/2 plus 1/2 will equal 1. 1/2 plus negative 1/2 will give you y to the 0. Anything to the 0 power equals 1. So this is a -1, this is a -1. -1 minus 1 equals -2, okay? So if you didn't get this right, that's no big deal. It's just, like I said, I think you get more if you actually tried it, and hopefully you'll remember now kind of how to work with this. Okay, so now I have my g prime of y squared. Hold on to your hats, folks. We're not even close to being done yet. So back to this. So I'm going to plug everything in. Cool. So we're all hunky-dory. So now I've plugged in my function x, and then there's my g prime squared. So we already did all that work. All good. Can I integrate this? No. So now we have to think of how the heck am I going to integrate this? Well, the first thing that I kind of notice that is intimidating me is that this stuff under the square root, there is a lot going on there. And there is also like a like terms, right? Because there's a 1 and then this -2. So I do actually want to take a second just to think about this and see if we can make life easier. So, okay, let's just focus on this part of the calculation for a second, okay? So now what I want you to do, again, I'm going to kind of walk you through this because I think you're going to get a lot more out of this if you try this versus just watching me. I want you to go ahead and distribute the 1/4, collect your like terms, and I want you just to stare at the problem for a second and see if you can see any way to rewrite or simplify that problem. That's the hint that I'm going to give you. I want you to come up with 2 different ideas before you hit play, because this is one of those things where, again, you're not going to get better at this if you don't try something. Even if it's not going to work, it doesn't matter. I just want you to try something, okay? So pause, give it a try, hit play when you're ready. Okay, so I am going to do this now. So I'm going to go ahead and distribute the 1/4, and now I can see that I have the 1 and the -1/2. So I'm going to combine those 2 things together. And so now I've got 1/4 y plus 1/2 plus 1/2, 1/4 y to the -1st. And okay, so what else can we do here? Well, the other thing I think of right away is I think, oh, I could take out the 1/4. So if you made it there, awesome. And so if I take out the 1/4, now I can see, okay, I'm left with this. Now, here's the deal. This should look kind of familiar to you. So think back to what we were just doing a couple minutes ago, right? Remember when we did this whole crazy calculation with this g prime y squared? So hopefully you wrote all this down. And sometimes, like, looking back at your old work, like if you actually expanded it and were really neat with it, it can provide inspiration on how to move forward. So what I think of here is when I look at this, what looks very similar? Well, what looks very similar is that I had something with a 1/4 in front, and then this was all squared. And when I blew this out, right, I got this expression here, right? So this and this are equivalent to one another. And so if I bring that back to just what I'm looking at right now, so the only difference between this expression now and this expression is that this has a minus sign and this has a plus sign. But look what we did with this, right? I also factored this. I factored this into this squared. And if I could write this as something squared, then I could actually take the square root of it, right? So there's kind of this big aha built into the whole thing. So what I'm going to do is I'm totally going to leverage this pattern here. So I want to check if you are getting this. So I want you to write down, how should I rewrite this expression? Write down what you think it is before I show you. So pause, hit play. Okay, so the way that we're going to write that is y to the 1/2 plus y to the -1/2, right? So this was y to the 1/2 minus y to the -1/2 squared. Since this is now a plus, this will be a plus here instead now, right? Okay, cool. So fun, cute, love it. Let's keep going. So we worked all this out. So now what I'm left with is this whole expression here has been condensed into this. And the good news about this is that I can actually take the square root of this, right? So if I can take the square root of this, what am I left with? So here's, again, another challenge I'm going to pose to you. So let's go ahead and take the square root. Okay, so I got rid of the square root. Here's what I'm left with. So I think you have enough information at this point to finish this problem. I would challenge you to finish this and just try to give yourself like breadcrumbs through the explanation, but try to finish as much of this as possible. So give it a try, hit play when you're ready. Okay, so I'm going to show you the rest of the solution now. So I am left with this expression here. So the first thing I notice is that the 2's can cancel out, and then I can rewrite this expression here. All right, so now what am I left with? I can't integrate this as is, right? There's two things being multiplied together. But I could multiply them, right, friends? We could 100% do that. So we are going to FOIL them out. And again, if you weren't sure what to do, then I want you to FOIL it out, and then I want you to hit play. So I'm going to go ahead and show you what it looks like to FOIL everything out. So this is what I get when I FOIL everything out. And you'll notice here that I have like terms, so I can actually rewrite this whole expression then as negative pi times the integral from 1 to 3 of 1/3 y squared minus 2/3 y minus 1 dy. Okay, and this is definitely something that we can integrate, right? And then the rest of this is just like the math. So there is everything integrated, and then if I plug in my limits of integration, so I'll give you a second. If you want to pause the video here to write anything down, go for it, because I'm about to show you the next part of this. So let me show you what it looks like to plug everything in. So I plug in the 3, I plug in the 1, and if I go through and I do everything, here are my calculations, and I'm going to be left with 16 pi over 9. Whew, all right. Never said that these were going to be easy, right? Okay, so that brings me to the end of this video. If you found this helpful, I'd love it if you hit that like button, maybe leave me a comment or subscribe. And otherwise, I am going to leave it at that, and I hope to catch you guys in another video. Bye.